So this is Lab 3, Massive Black Hole, Physics 2211. So the problem that we're looking at is we don't know the mass of the black hole. We were given the mass of a star, we were given a distance to a black hole, but we don't know the mass. And we don't know the net force for the black hole. How are we going to find it? Well, we're going to use Python to establish velocities, momentum, and ultimately the net force on the star. And my final result, what I got for it, was that it was 3.1824 times 10 to the 31st kilograms, which lined up with what Webdesign gave us. So the given material was, my mass of the star was 2.39113 times 10 to the 27 kilograms. Everybody's was different. The time step should be the same for everybody, which was 86,400 seconds, and the black hole position was, as you see there. So the physics that are behind this that we're going to use is we're going to apply Newton's second law, which said that basically when you rearrange the variables, F net equals dp over dt, and also F net is going to be equal to the sum of its parts, the parallel part and the perpendicular part. We're also going to use Newton's law of gravitation, which is gm1m2 over r squared. That's going to be the net force. So when you rearrange that equation, you have the magnitude of the net force times the radius squared, which is going to be the difference between the star and the black hole, position-wise, divided by g times the mass of the star. So, real quick, the relationship between F net and dp dt, they're not the same. F net is the force that's going to be applied to the object. dp dt is the change in momentum over the change in time for the object. Now F net is what's causing that change in momentum. It's causing that change, and so F net is the cause, and dp dt is going to be the effect. F net parallel also in the situation, since we're going in a curve. In an elliptical motion, F net is not zero. That's caused, you can see that from the curving motion. So the mass of the black hole calculation, you can calculate that from any given point on the star's elliptical motion. I decided to put it in my code so it was easier for Python to calculate it, and I didn't mess it up at all on any kind of calculation with my calculator. G is a constant. The black hole position was given to us, and then our radius is going to be the difference between the star position at any given point in time. I put this at the end of my code, so it was the very last position of the star, and the difference between the black hole position and that star position. And then the mass, when we rearranged our equation, gave us the magnitude of the net force, which was calculated at the end, Python code times radius squared divided by g times the mass of the star. And so that's how we calculated it, and what the actual result of that was 3.1824 times 10 to the 34th kilograms. This is what the module looked like when you ran it. Really wasn't any point in showing you it moving, because you know how it's going to move. And then those are the arrows, with the red arrow being the parallel force, the yellow being the net force as a whole, and blue being the perpendicular force. Right here from these arrows you can tell already that F net is equal to the parallel plus the perpendicular, because when you add the two vectors together it's going to be going straight down the middle of them, which our yellow one is. Also, there really wasn't any need to show you guys any of the code for it because we all have the same code. So the only thing that I had to change in my code to make mine look different from anybody else's was the arrow scale. My arrow scale was 4 times 10 to the negative 12th. That was so that you could actually see everything. Instead, if I didn't change that, all you would see was massive arrows. You wouldn't see anything else. So what if? So what if the star that, or the black hole that was in the middle, was replaced with a new one, with supposedly a different mass, but the motion never changed, and neither did the only force that was acting on it was a force from a black hole. No, you could not tell the difference between the two. Based on our calculations, we were only looking at numbers, so the mass that we would get if the motion of the object is not changing would be the exact same, even if it was a different black hole that was replaced in there. Really, if the motion is going to stay the same, if there is a different mass, it's going to be so small that it's not going to be a significant enough change for our calculations to show any different. And that's it. Thanks.